In this stage of the course, we're now going to look into the properties of light, so thinking of light as a wave. So first we're going to open with a question. Light is travelling through a vacuum, is incident at some angle theta on a block of glass, which, if any, of the following properties of the light will change moving into the glass. So will it change speed, direction, frequency, or wavelength? Pause the video and think about your answers. We'll talk about them shortly. Moving into the glass, the light will slow down. This is the interaction of the electric field of light with the electrons in the glass. The light will also refract, so we would expect its direction to change, and we'll talk more about that as we go through this part of the course. The frequency, however, will remain unchanged, and we'll talk more about why that is shortly. And the wavelength will also change as well. Now remember, there's an interdependence between the speed, frequency and wavelength, so if one of them changes, at least one of the others has to change, but in this case the frequency remains unchanged. The reason for this is because the waves must remain continuous at the interface. If you remember the waves moving between two pieces of string of different densities, we had that continuity requirement there. The same is true of a light wave. So reflection and refraction rely on a property of materials known as its refractive index. This refractive index is the ratio of the speed of light in the vacuum and in the substance. So we can find the refractive index of any material by dividing the speed of light by the speed in that material. This means that a refractive index will be 1 or greater. So we would expect to see a ray diagram that looks like this, where the incident ray strikes the boundary at a particular angle θ1 to the normal at the surface. It is reflected at the same angle on the other side of the normal, while part of it will be refracted moving into the other material. The frequency of light is unchanged. Remember, we said that was a continuity requirement. What that means is if the speed has slowed down, that means the wavelength must be shorter to keep that frequency constant. So we can find the wavelength in the new material by dividing the wavelength in a vacuum by the refractive index of the material. Whenever light is incident on an interface, part of it is always reflected, while part of it is transmitted and refracted. All of the angles that we have in the system are measured relative to the normal, this perpendicular line to the surface. The principle of refraction is subject to Fermat's principle, and this says that the light taken by the path between 2 points is such that the travel time is always a minimum. And this isn't necessarily the shortest path. When we're talking about reflection, where the light remains in the same material, this will be the shortest path, which involves reflecting off the surface, while the refracted ray, again, also takes the least time, but it isn't necessarily going to be the shortest path, and we'll come on to why that is shortly. Let's first consider reflections. So what we've modelled here with this animation is all the different ways that a light ray could possibly reflect to get from point A to point B. And what we're showing here is what would happen if we had different angles of incidence and angles of reflection. So considering the light ray travelling in the same medium, going from A to B, and the point P of reflection moves where the normal is. What we're saying in this diagram is that the distances APB and A'PB are all the same. Because the light is staying in the same medium, i.e. above the plane of the interface here, that means its speed is going to be the same moving from A to P to B. That means we have the shortest time when this path is the shortest it can possibly be. And the shortest it can be is when this A'PB line, this orange dotted line, is a straight line. So that means that the only condition which satisfies that is when the angle of incidence equals the angle of reflection. However, this same demonstration doesn't work for refraction. So we need to think of a different principle. Let's now consider the light moving from the material with refractive index n1 to refractive index of n2. The angle of incidence in this case is θ1 and the angle of refraction is θ2. In this exercise, what we'd like you to do is show that the quickest path from A to B requires this equation, that n1 sine θ1 is n2 sine θ2. The best way to do this is to come up with an expression for the time taken to get from A to the interface and then from the interface to B, using these distances and the speed of light in each material. Pause the video and we'll come back to your solutions shortly. Okay, so let's remember that the speed of light in any material, v, is equal to the speed of light in a vacuum divided by the refractive index, n. That means that we can find a time for the light to travel from A to B. So let's take this stepwise. The overall time is going to be the distance from A to the interface, which is a squared plus x squared square rooted. So that's just using Pythagoras theorem. And we divide that by the speed v. So multiply by n1 over c. That's what this is giving us here. Then we can find the time on the other side of the interface, which is b squared plus d squared square rooted. Now what we do is we minimise with respect to x. In order to minimise, we find the first derivative, and once we've got our first derivative, we can say that we have n1 over c times x over the square root. That is x, the horizontal distance, divided by the path length, which is equal to the sine of the angle θ1. And the same here, where we have the horizontal distance d divided by the path length in this medium. That again is sine θ2. So we can substitute these values in, and then what we can do is set a minimum when this is equal to 0. Remember, with calculus, if we want to find the minimum, we find the first derivative, set it equal to 0, and solve for our variables. That means that n1 sine θ1 minus n2 sine θ2 is equal to 0, or, to put it another way, n1 sine θ1 equals n2 sine θ2. This is a principle we know as Snell's law, and Snell's law tells us how these angles vary with the refractive index n. Practically, what this means for us is that light entering a medium with a higher refractive index is bent towards the normal, while light entering a medium with a lower refractive index is bent away from a normal. And we see this path here for light moving into glass and then moving back out of glass again. A useful concept at this point is the use of reflection and reflectivity. So when we think of light being incident perpendicular to the surface, we get this reflectivity ratio defined by the intensity ratio of the two rays. So we have the incident beam I0 and we have the transmitted beam I. And we can find an expression for each of these intensities relative to the incident beam and the reflectivity ratio. This is simply a ratio of the reflected intensity to the incident intensity. This can additionally be defined in terms of the refractive index n1 and n2 in this manner here. And again, we can find the transmissivity by 1 minus the reflectivity ratio. This expression can be derived, however there's no need to do it at this point, but it is a useful thing to bear in mind that we've seen something like this before. When we looked at the waves passing along a string, we had a power ratio, a transmitted to reflected power ratio, using impedances. In this instance, we're using refractive indices, where the impedance to light is 1 over the refractive index. Practically, we can interpret this as a lower refractive index being analogous to a stiffer material. So a lower refractive index offers a higher impedance, which means we have a higher phase velocity, and that's in line with our expectations. A lower refractive index has a higher speed of light moving through it. In summary, refractive index relates the speed or the wavelength of light in that medium. The path of the light ray fundamentally minimises the travel time moving through the material. What that means for reflection is that the angle of reflection is equal to the angle of incidence. But when we go for refraction, when the light crosses the boundary into a material of a different refractive index, we are subject to Snell's law, and we consider the sign of each of the angles with the refractive index. Finally, we introduce this idea of optical impedance Z being 1 over the refractive index n. And that is a useful concept for thinking about how light interacts with matter. It's outside the realm of this course, but it will be useful for you when you do your geometric optics course.